Yes, good morning students. How are you? Today I will go to start the revision chapter solutions. Very important chapter for second PUC portions in physical chemistry is solutions. Usually it carries 7 marks in board exam. Carries 7 marks in board exam. Out of this 7 marks, in part A, usually first question from solution chapter that carries 1 mark, and second question in part A also carries 1 mark. Weightage for this chapter in first part, that is the part A, 2 marks. First question in your question paper usually begins with solution chapter question, and second question in annual exam that also consists questions based upon solution chapter. And in part B, where it carries 2 marks question, whereas a part C, pure inorganic chemistry, 3 marks question. It does not consist of the solution chapter. And part D, usually physical chemistry portions. Question number 28. Usually solution chapter questions, it consists of 2 sub questions. 28A, that is usually numericals, carries 3 mark, and 28B, that carries 2 mark. Total 1 plus 1 plus 3 plus 2, that is 7 mark. Maximum weightage, that is 7 mark. In our question paper, usually 10% weightage out of 70 marks, that will be in this chapter only. That is simplest chapter because it is in connection with your first PUC portion, some basic concepts of chemistry. If you thorough with first PUC chapter, some basic concepts of chemistry, solution chapter is so simple. Usually the solution chapter in KCET and NEET exam and JEE Mains exam, usually it carries 1 question. The solution chapter that I can segregate into 4 different parts. That is the first part, that is a part A, that is a simple concept, that is the types of solutions, and concentration of the solution, methods used to express the concentration of the solutions. Usually in concentration of the solutions, we have the terminology like molarity of the solution, molality of the solution, and mole fraction, and percentage of the solution. There is weight by weight percentage or mass by mass percentage, and volume by volume percentage and weight by volume percentage and parts per million. Parts per million. In part A, in introduction part, we have different types of the solutions, methods used to express the concentration of the solutions in terms of molarity, molality, mole fraction and percentage of the solutions like mass by mass or weight by weight or volume by volume or weight by volume and parts per million. This is in part A. In part B, or second part of this solution chapter, we can have this vapor pressure of the solutions. Vapor pressure of the solutions. In this vapor pressure of the solution, it is represented by suppose Vp. We can have vapor pressure of the liquids, vapor pressure of the liquids and vapor pressure of the solutions, vapor pressure of the solution. Here it based upon Rolle's law. Very important. Rolle's law and its applications, limitations, and here concept of ideal and non-ideal solutions. Concept of ideal and non-ideal solutions. Along with examples. Along with examples. And solubility concept. Solubility concept. And effect of temperature, pressure and nature of this solvent and nature of the solute. Nature of the solute and nature of the solvent. And further extension to Henry's law. Henry's law and azeotrophic and geotrophic mixtures, azeotrophic solutions. Azeotrophic mixtures with minimum boiling point and maximum boiling. Minimum boiling point and maximum boiling point. These are some very important concepts that we have to study in second part of the solution chapter, that is vapor pressure. And third part is very important, that is a part C. Part C. Usually 28A. That question will appear in part C. Especially numericals, but is colligative properties. Here we come across relative lowering of vapor pressure, elevation in boiling point, elevation in boiling point, and depression in freezing point, depression in freezing point, and osmotic pressure. Osmotic pressure. You have to study graph concept, important applications, and numericals based upon this 4 important colligative properties. And last part, that is a part D. Here you come across definitions of the terms: isotonic solutions, hypertonic solutions, and hypotonic solutions. And abnormal molecular mass, abnormal molecular mass. Here you come across association and dissociation. Association and dissociation. Here we introduce one more myth, that is a term, want of fact. This is about the brief introduction of this solution chapter. Part A, basic terminologies. Part B, vapor pressure. Part C, colligative properties. Part D, concept, different definitions along with examples and applications. What do you mean by solutions? In our first PUC, first chapter, we studied about the basic concepts like elements, compounds, mixtures. Elements, compounds, and mixtures. Now, what do you mean by elements? You know that these have unique properties, each are independent in physical and chemical respects. Whereas the compounds, whereas the elements, they combine to form the compounds under suitable conditions by means of chemical bond formation. Once the compound is formed from its respective constituent elements, the property of the compound and property of the elements are entirely different, and different types of the chemical bonds would be formed. And what do we mean by the mixtures? Here the mixture, they are formed by 2 or more constituents. Whereas the mixture properties, that depends upon the constituent species. The mixtures are further classified into homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures and heterogeneous mixtures. Heterogeneous mixtures. The further classified mixtures and further colloidal solutions. Homogeneous mixtures, heterogeneous mixtures, and colloidal solutions. When you add sugar and water, when you add oil and water, you have the difference. When sugar crystals are added to water with constant stirring, Then particles of the sugar or the solute, they disperse in water, they forms the homogeneous solution. Here the particles are invisible, solute particles are invisible. We can't identify the particles because the size of the particle is too small. Whereas in heterogeneous mixture, when you mix oil plus water in hard glass test tube with constant shaking, then we can observe separate oil layer and separate water layer. Due to the smaller density of the oil compared to water, oil floats on the surface of water. We can easily identify the oil layer and water layer. They can't mix up. Under suitable condition, we can have the methodology to mix up. Whereas the colloidal solutions, you can observe some of the solutions like your maza or toothpaste or gum or gel. In these cases, the solution is said to be homogeneous in nature, but it is in heterogeneous phase. It is homogeneous in appearance but heterogeneous in phase. Then we come across in separate chapter in surface chemistry, this is colloidal chemistry. Now homogeneous and heterogeneous. Now homogeneous solutions. Now solutions are homogeneous mixtures of solute and solvent. Solution, it is a homogeneous mixture of two components or more than two components, solute plus solvent. When it mixes up in homogeneous fashion, then it gives the component called as a solution. Solution is a homogeneous mixture of two or more components. Usually our syllabus consists of binary mixtures. In binary mixtures, we have two component system. In binary mixtures, we have two component system. One component is solute and another component is a solvent. Solute and solvent. The homogeneous mixture is called as a binary mixture. Now what do you mean by solute? When sugar crystals are added to water, then sugar crystals dissolves. The portion of the solution which is present in smaller quantity, that has ability to disperse in the medium, that is called solute. That is what is solvent. Solvent is the medium which has ability to disperse or dissolves in its vicinity. That component is called as a solvent. Solute may be either solid phase or liquid phase or a gaseous phase. Similarly, solvent is also solid phase or liquid phase or gaseous phase. Depending upon the nature of the solute and the nature of the solvent, solutions are classified into different classes. That is why it is called classification of the solutions. Classification of the solutions. Whereas types of the solutions. Types of the solutions. Types of the solutions. It all depends upon nature of the solute and solvent. Whereas a solute may be either solid phase or liquid phase or gaseous phase. may be either solid phase or liquid phase or gaseous phase. If the solid phase, this is solvent phase, and it is nature of the solution. Nature of the solution. With example, if solute is solid, solvent is also solid. Whereas solid and solid solutions. For example, alloy systems. Whereas a brass or bronze or alnico, gunmetal, bell metal, rose metal. In all these types of the solid solutions, two or more number of the solid metals after their melting point and mix up, then it gives the homogeneous solution. After solidification, it gives the clear solution, that is called solid solution. Whereas except the solid solutions, the remaining solid in liquid or solid in gas or liquid in liquid, liquid in solid, liquid in gas, or gas in solid or gas in liquid or gas in gas, they can be obtained by means of different methods. But solid in solid, that is obtained only after the melting point of the solid. Whereas suppose copper and zinc, both separately upon heating, both melting points gives the fluid mass. After mixing the fluid mass in one container and mixing thoroughly in order to get the homogeneous solution, after solidification, then it gets the solid product, that is called alloy. Therefore, alloys are the good examples. Alloys are good examples. Any alloy is a good example. Whereas gemstones, colored stones, colored glasses, they are also good examples for this solid solution. Whereas solid in liquid and solid in gas. Whereas solid in liquid, you know about the salt solutions, sugar solutions. They are good examples where the amount of solute is very small or the medium is in larger quantity. Whereas the sugar plus water, that forms the homogeneous solution. Whereas sugar plus water. Sugar plus water or salt plus water. Whereas a solid in gas, this type of the solutions, these are all good examples for the binary solutions. Whereas a liquid in solid and liquid in liquid and liquid in gas and gas in solid and gas in liquid and gas in gas. There are different types, 9 different types of the solutions. Whereas a solid is a solid phase and gas is the solvent phase. Means gas is present in larger quantity and solid is present in a smaller quantity. Whereas a liquid in solid, liquid in liquid. Whereas the ethyl alcohol and water mixture, ethyl alcohol plus water, ethanolic solution, ethyl alcohol, both are in liquid phase. Whereas a liquid in gas, whereas you know about the mist or fog, whereas when you spray the liquid water in air, then this is mist or fog, good example. Whereas a gas in solid, gas in liquid and gas in gas. Usually air, that is a mixture of this nitrogen and oxygen, where they are homogeneous in nature, homogeneous in appearance. Whereas remaining examples you have to study, whereas solid in gas, liquid in solid, and liquid in gas, and liquid, that is gas in solid and gas in liquid. I mentioned few examples. In your surroundings you have to observe what about the different types of the solutions. Whereas both are liquids, ethyl alcohol and water, whereas the gas in gas, whereas the air is a good example for gas in gas type of the solutions. These are the different types of the solutions. Now, small information, sugar in water. Solubility of all solid substances in liquid medium, that mainly depends upon certain factors. Again, I will explain in solubility factor. It depends upon nature of the solid. Whereas crystalline substances are usually soluble in aqueous medium or water medium types of the solutions. Most of the examples that we observe in nature, that belongs to any one of this category. For example, you know that soft drinks, whereas in soft drinks usually they are passing carbon dioxide under high pressure, whereas the carbon dioxide is a solute, whereas the water or liquid medium is the solvent. Therefore, soft drinks are good examples where gas in liquid medium is there. For example, your natural water bodies like lake water, river water, ocean water, whatever it may be. Whereas the air contains oxygen, small part of the oxygen has ability to dissolve in water bodies, either lake water or river water or natural water bodies, which is exposed to air. Whereas the solubility of any gas in liquid medium or water, that mainly depends upon pressure and temperature. Increase in pressure increases the solubility, increase in temperature decreases the solubility. That is why marine system that exists, because in marine system the dissolved oxygen present in water bodies that is used or consumed by means of this aquatic organisms. That is the application of our all these problems. Whereas remaining examples that you can study. Now, methods used to express the strength of the solution. Express the concentration. Methods used to express the concentration of the solution. This is often called the strength of the solution. Whereas the given amount of the solute is dissolved in specific quantity of the solvent, then we can express the concentration factor either in terms of molarity or in terms of molality, whereas the capital M stands for molarity, small m stands for this molality. In addition to this, we have another terminology, normality, and also we have another terminology, that is the formality of the solution. Then we have weight small w divided by capital W, or volume divided by volume percentage, or mass divided by volume percentage, and parts per million. These are the different methods used to express strength or concentration of the solution. Now first one is molarity of the solution. In your first PUC chapters you studied about the mole concept. What is mole? Mole is nothing but gram molecular mass of the substance. Molecular mass has no unit. It is mere number. When it is expressed in terms of gram, then it is called gram molecular mass of the substance. When gram molecular mass of the substance is present in given volume of the solution, then we can call it as molar solutions. Usually it is expressed in terms of molarity of the solution is denoted by capital letter M. Number of moles of the solute when dissolved in 1 liter of the solution, then it is called molarity of the solution. Number of moles of the solute. Number of moles of the solute. Number of moles of the solute, that is usually expressed in terms of gram, divided by volume of the solution. Volume of the solution, that usually expressed in terms of liter. Number of moles of the solute divided by volume of the solution in terms of liter, that is usually expressed in terms of grams per liter. Grams per liter. Then how to express the quantity of the substance in mole? For example, for a simple example, you know about the sodium hydroxide. Sodium hydroxide. Sodium hydroxide. Molecular formula NaOH. Molecular mass for sodium 23 atomic mass, oxygen that is 16 atomic mass, hydrogen that is 1 atomic mass, total that is 40. Molecular mass of sodium hydroxide is 40. Gram molecular mass of sodium hydroxide, gram molecular mass of sodium hydroxide. Gram molecular mass of sodium hydroxide is 40 gram. Gram molecular mass of sodium hydroxide is 40. This implies that 40 gram of sodium hydroxide corresponds to 1 mole of sodium hydroxide. 40 gram of sodium hydroxide corresponds to 1 mole of sodium hydroxide. When 1 mole of sodium hydroxide or 40 gram of the sodium hydroxide is dissolved in 1000 ml of the solution, then it is called 1 molar solution. Then 40 gram of sodium hydroxide when dissolved in 1000 ml of the solution. 1000 ml of the solution. 1000 ml of the solution. Then it is called 1 molar sodium hydroxide. 1 molar sodium hydroxide. In our exams, they may not give 40 gram and may not give 1 liter. Then how to solve the problems? If 4 gram of the sodium hydroxide is dissolved in 100 ml of the solution, then how to calculate molarity of the solution? One method, you have to convert number of moles of solute. 40 gram 1 mole. If it is 4 gram or multiples of 40, then you have to calculate. 4 gram means 0.1 mole. If it is 8 gram, then 8 by 40. If it is a 10 gram, 10 by 40 moles. Therefore, quantity of the substance in gram divided by molecular mass, that gives the number of moles. Quantity of the substance in gram divided by its molecular mass, that is equal to mole of the substance. How do you calculate the mole of the substance? Mole of the substance. Mole of the substance. Any substance that you have to given in exam. Mole of the substance is given by quantity of the substance in gram. Quantity of the substance in gram divided by its molecular mass. Divided by its molecular mass. Divided by its molecular mass. If quantity of the substance is 40, then molecular mass is 40, then the amount of the substance is what mole? Mole is the quantity of the substance. Suppose if it is a 8 gram of the NaOH is present, then you have to convert into moles. Therefore, that is 8 by 40, that is 1 by 5, that is equal to 0.2 moles of the sodium hydroxide. If 8 gram of the sodium hydroxide present in 1000 ml, then it is 0.2 molar solution. Then similarly, you can have capacity to calculate the molarity of the solution. Molarity of the solution. If it is a 1000 ml, no problem. If it is 500 ml or 250 ml or 400 ml or 100 ml is given, then you have to convert into 1000. That is, you have to express. Suppose this is if it is 1000 ml directly given, then that is equal to 1 liter. If in problem it is mentioned there is 500 ml, then that is 500 divided by 1000, that is 0.5 liter. In our problem, if it is 250 ml is given, then that is 0.25. If it is in problem, it is 100 ml of the solution is given, then that is 0.1 liter of the solution. How to calculate? That is the given volume divided by 1000 ml. Given volume divided by 1000 ml. That is how to calculate in terms of liter. Given volume is 500 divided by 1000, that is 0.5. If given volume is 250 ml, 250 divided by 1000, that is equal to 0.25 liters. Given volume is suppose 100, then 100 by 1000, that is 1 liter. If the given volume is suppose 400 ml, 400 ml, then that is a 400 ml divided by 1000. That is equal to how much? That is 0.4 liters. 0.4 liters. Is it clear? Therefore, the given volume by 1000, if it is not 1000 ml in your problem, you have to calculate volume corrected to 1000 ml. In numerator, suppose if it is not in one given molecular mass, then you have to convert into moles. The given quantity of the substance divided by the molecular mass and given volume of the solution divided by 1000 ml. Or you can use one more formula that you already studied, whereas grams per liter is equal to molarity into molecular mass. Molarity into molecular mass. By using this method also, you can calculate the concentration in terms of liter, that is in terms of molarity. Whereas G stands for the given quantity of the substance, L stands for the volume of the solution in terms of liter, you have to correct it to liter. Then keep M as such and molecular mass of the substance, that you should know by knowing the formula of this chemical compound. By using this method, you can calculate the molarity of the solution. Because by this method, G by L grams per liter is equal to molarity into molecular mass. Molarity into molecular mass. Whenever G is given and L is given and molecular mass you know, then you can calculate the molarity of the solution. Now, what is molarity? Molarity is one of the method used to express the concentration of the solution or strength of the solution. The number of gram molecular mass of the solute present in 1000 ml or 1 liter of the solution is called molarity of the solution. It is usually expressed in terms of grams per liter. Now, very important, when you prepare the different solutions in terms of molarity in different temperature ranges. Suppose today's temperature is 25 degrees Celsius, tomorrow's temperature is 26 degrees Celsius, day after tomorrow's temperature is 27 degrees Celsius. Then my question is whether the strength of the solution is always same. No, because it depends upon temperature factor. Very important. Some of the concentration terms where the denominator has volume factor, that volume that depends upon temperature. Concentration factor which depends upon volume, they all are temperature dependent. Now, very important, molarity depends upon temperature. Molarity depends upon temperature. Molarity depends upon temperature. This is very important. Molarity depends on temperature. Depends on temperature. Molarity depends upon temperature. Confusion, sir. Only molarity depends upon temperature. No. The concentration factors which contains volume factor, all that depends upon temperature. Whether directly depends on or inversely depends upon temperature. Now, in denominator, usually volume factor is in denominator. What is the effect of temperature on volume? Increase in temperature, whether volume increases or decreases. What is the relationship between volume and temperature? Higher is the temperature, when temperature is increased, volume correspondingly increases. When temperature decreases, then volume decreases. That you know about in Charles' law. Whereas at constant temperature, volume is directly proportional to temperature. Therefore, whenever temperature is in numerator, then it is directly proportional to. When the temperature in denominator, it is inversely proportional. Therefore, it depends upon temperature. One more is molality, small m. Small m is molality. Capital M is different from small m. Capital M is different from small m. M is equal to molality. This is LITY, that is RITY. Now, molality is represented by small letter m, molarity is represented by capital letter M. What is molality? Number of moles of the solute present in 1 kg of the solvent. Number of moles of the solute present in 1 kg of the solvent. Number of moles of the solute. Number of moles of the solute divided by 1000 gram of the solvent. 1000 gram of the solvent or 1 kg of the solvent. 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 Now number of moles of the solute divided by 1 kg of the solvent. If 1 mole of the solute is present in 1 kg of the solvent, then it is considered as a 1 molar solution. 1 molar solution. 1 molar solution. Suppose if 40 gram of the sodium hydroxide, same example, suppose when it is present in 1 kg of the solvent, 1000 gram of the solvent, then it is considered as a 1 molar sodium hydroxide. Very important. Here both are fixed. 40 gram of sodium hydroxide is fixed, 1000 gram of the water is also fixed. You place 1000 gram of water in one hard glass flask, then add 40 gram of the sodium hydroxide with constant stirring, then it dissolves and it gives a homogeneous and clear solution, highly transparent solution. You can label as a 1 molar sodium hydroxide. But how do you prepare 1 molar sodium hydroxide solution? In order to prepare 1 molar sodium hydroxide, you are not supposed to place 1000 ml of water. You place less than 1000 ml of water, say about 500 ml of water, add 40 gram of the sodium hydroxide, stir well, then it gives the homogeneous solution. It may be exothermic or endothermic, some cases. When sugar crystals are added to water, glucose powder is added to water, you can feel endothermic process. But when you add sodium hydroxide pellets in water, then heat energy would be liberated. Then it is exothermic process. Then keep at 25 degrees Celsius temperature or cool to laboratory temperature and transfer into 1000 ml measuring jar and make up the solution up to 1000 ml. Here the volume of the water required will be less compared to 1000 ml. Therefore, here it is volume of the solution is fixed in molarity, but quantity of the solvent is fixed in molality. But whether molality depends upon temperature. In denominator, we does not have terminology like liter, volume factor. Volume depends upon temperature, but amount does not depend upon temperature. Therefore, in both the cases, numerator and denominator, we does not have any volume factor, and hence molality is independent of temperature. Whether increase in temperature or decrease in temperature, the molality strength of the solution is always fixed.